thanks a lot to the people who actually set the stage. So that is really great because now I can actually concentrate and jump into the nitty-gritty details, the physics. So what about cosmic rays? Let's get started with this. I would like to understand how you actually make galaxies blow galactic winds, because we have heard this morning, this seems to be one of the essential points that we would like to solve to understand galaxy formation. Now, I would like to start with this slide, and that shows the star conversion efficiency. So let's see whether this pointer works. Yes. So this shows the amount of stars divided by the halo mass as a function of halo mass from scales of dwarfs to spirals to giant galaxies. Now, for small galaxies, the cooling time is shorter than the age of the universe. So you would expect all the gas in these halos cools and converts to stars. That is not what is happening. At most, we can convert 20% of the baryons into stars. And this only happens at the scale of the Milky Way. If you go to smaller galaxies, less than 1% of the available gas is converted to stars. That's a big puzzle. Why is this? If you move to the sort of large galaxies, the same happens, but potentially for a different reason. And understanding this physics is key in my mind to understand galaxy formation. Now, the current model means some kind of stellar feedback solves this faint mass end, and some kind of feedback, potentially provided by AGNs or supermassive black holes, solves the bright end of galaxy formation. But what is stellar feedback? Now, clearly, we have supernovae going off. Supernovae thermalize the interstellar medium and can push out the gas. At least the simulations that we have run so far were not enough to sort of push out the gas. They are able to self-regulate the interstellar medium. Now, 10 years ago, people said, okay, supernovas are not enough, but there is radiation. Radiation can photoionize the interstellar medium, and they can basically have a radiation pressure that kicks the atoms. Problem solved. And people have sort of put in this physics. Oops, I'm sorry. So let's see, is this working? Okay. People have basically put in this physics, and lo and behold, the subgrid model solved the problem. But high-resolution simulations that actually do the proper radiation transfer saw that this is not enough, except perhaps for the most massive starburst systems. And then a process that people have overlooked so far, cosmic rays, got into fashion. Potentially, the pressure provided by cosmic rays can drive these winds. Now, what are cosmic rays? Well, cosmic rays is a non-thermal population of particles spanning a wide range of energies, 12 decades in energy and 33 decades in flux. And we basically see there's a beautiful power law where two features. There's the knee, where the spectrum steepens a little bit, and there's the ankle, where it flattens a little bit. Now, we are concerned with the pressure contained in cosmic rays, and this sits at GeV energies here. And if you calculate the amount of energy density contained in cosmic rays, then you find that this is equal to that in magnetic fields, the thermal gas, and turbulence. So clearly we can't neglect it, and we need to take this into account. All right, so we have just published a review, and this may be the biggest review ever published in this journal, because we didn't just review the field, so we didn't just read all 1,000 papers and cite them, but we provide a pedagogical, sorry. This is actually, I should probably, this is on? Okay. So this is actually a pedagogical introduction. So if you want to sort of learn about the plasma physics, and I will dive into this a little bit here, then please go and read this review. Now, what's the problem? So we would like to simulate galaxies, Milky Ways, ideally in a cosmological environment, but we have to resolve the gyro orbit of cosmic rays, and the gyro orbit of a GeV cosmic rays in a micro-Gauss field is 10⁻⁶ parsecs, a quarter of an AU. So these are planetary scales in a cosmological environment. That's impossible, clearly. So we have to sort of develop a theory, a fluid theory, for a collisionless, non-Maxwellian component. What's the physics that this fluid theory has to do? Let's start very simple. We make a time change. So you are right now a student back in your lectures, and you're listening to electrodynamics. There's a uniform magnetic field. There's a charged particle that spirals around this magnetic field. That's easy. Make it a little bit more complicated. Add a perturbation to this magnetic field, a so-called alphane wave. Now, as you can see, this goes down, up, and down. Now first, the first quarter of the orbit where the cosmic rays goes into the board, it experiences a Lorentz force, V cross B, which is decelerating. And that's what you can see here. Oops. I'm gonna switch here. Now the second half of the orbit, the cosmic rays comes out of this orbit, the magnetic field goes up, and again, there's a decelerating Lorentz force. And the last quarter of the orbit, again, the Lorentz force is decelerating. Okay? Now, in the frame of the alphane wave, the magnetic field is stationary. It doesn't change. That means there's no electric field in this alphane frame. Now, we have worked out the Lorentz force of these cosmic rays, and we saw that this is always decelerating along the entire orbit of the cosmic rays. And obviously, it depends on the relative phase of these cosmic rays. So, if we have a decelerating Lorentz force for this sort of setup here, if we have a phase shift here, we have an accelerating Lorentz force, and the parallel momentum increases. Now, only electric fields can do work on particles. Remember your ED classes. So that means only electric field can change the energy of a particles. In the alphane wave frame, where the electric field is zero, the cosmic ray energy is conserved. That means p squared is constant. If you decrease your parallel momentum, you must increase the perpendicular momentum. And this increases the so-called pitch angle cosine, so that's the angle between the magnetic field and your momentum vector. So this is the idea how you can actually change the angle between a cosmic ray momentum and a magnetic field, and how you basically make the cosmic rays change the sort of velocity with which they move along the magnetic field. Okay? And clearly this only works if you have a resonant process where the length, the alphane wave, is equal to the cosmic ray gyro radius. And that is basically you Doppler shift the MHD frequency, and this has to match n times the cosmic ray gyro frequency. All right, if you then have cosmic rays interacting with a train of alphane waves, you can basically change the velocity with which the cosmic rays move along the magnetic field. You don't change the intrinsic velocity, they still move with the light velocity, but the effective velocity is changed and is slowed down in this particular plot here. Now, there's a second development in the 60s, the cosmic ray streaming velocity. So if cosmic rays move faster than the speed of the alphane waves, they amplify these alphane waves resonantly. Now, I've just told you how these alphane waves are able to scatter the cosmic rays, they slow them down until they move with the alphane waves, so they isotropize in the frame of these alphane waves. And then you have different wave damping processes that transfer effectively cosmic ray energy and momentum to the thermal gas. You start with cosmic ray energy. This is deposited into alphane waves. These are damped and heat the thermal gas. At the same time, they're slowing down the cosmic rays. And this is exactly how your collisionless particles interact with the ambient gas. Now, the cosmic rays exert a pressure not by scattering on individual particles, but by interacting with electromagnetic waves. And if you have a weak wave damping, you have a strong coupling because there is a high level of alphane waves available to scatter cosmic rays. So the result is that cosmic rays stream with the waves. if there's a strong wave damping, there are less waves to scatter cosmic rays, and there's cosmic ray diffusion that prevails. So you have now three processes. You have advection of cosmic rays along the magnetic field. You can have diffusion of cosmic rays, and you can see this Gaussian. And finally, there's streaming, where the cosmic rays stream with the alpha waves. Reality is a superposition of all these three processes. All right. Now, we want to model galaxy formation. So that means we have to model cosmic ray transport in these galaxies, and this means we have to model the interactions of cosmic rays in the warm, hot phase. So this is nonlinear Landau damping, and in the neutral and coldish phase, and ioneutral damping in this case prevails. It's very strong there. So this requires resolving the multi-phase structure of the ISM, and Timo and Thomas developed this CRISP framework, and you can see this beautiful galaxy that comes about there. What is this? Well, we couple cosmic ray physics to feedback physics and to resolve the multi-phase structure of the ISM. One by one, you need to follow the non-equilibrium cooling of at least 12 species, the full hydrogen, atomic and molecular chemistry, helium chemistry, and the first ionization stages of the cozy elements for the low temperature cooling. And you need to model the electric heating by dust. You need to follow the radiation using a radiation transfer. So this feedback part has an improved supernova treatment, which is manifestly isotropic. I can tell you that's not trivial at the resolution we can afford for simulating these galaxies. We have to account for stellar winds. And again, his model uses a radiation transfer for the far UV, NUV, and the optical radiation fields using a reverse ray tracing, including dust, including metal enrichment. And finally, the cosmic rays use a novel cosmic ray hydrodynamics, similar to what radiation hydrodynamics has done, which includes a coarse graining of the plasma physics I just explained to you. Cosmic ray ionization is important because this impacts the chemistry of forming molecules and all these cosmic ray microphysics things. So in particular, we follow the energy density and the flux of cosmic rays and self-consistently compute the diffusion coefficient. All right. Now, after all this works, one of these galaxies is run with cosmic rays, the other one without. Which one is which? Well, you shouldn't see a lot of difference. The right one, the left one, sorry, is run with cosmic rays, the right without. Why do cosmic rays not affect the interstellar medium? Well, because in this phase, ioneutral damping is very strong. It wipes out all the alpha waves so that cosmic rays cannot really scatter and are maintaining a very smooth distribution. Now, can we forget about cosmic rays? The answer is, of course, no. And the left-hand side is a simulation with cosmic rays, the right-hand side without, and that's now the surface density. Let's get this started. And you can see, indeed, after this initial starburst that comes from the initial conditions, there's a completely different history. On the right-hand side, clearly supernovae and radiation can self-regulate and drive fountain flows. But it does not drive a wind, or very weak wind in particular, while adding cosmic rays makes the wind basically move gas out from these galaxies. And this is actually even more dramatic by looking at the temperature. And you can see there's explosions happening right-hand side that heat up the CGM. But then once this sort of fountain flow establishes, the CGM is heated to very high temperatures, 10 to the 6 and larger, while on the left-hand side, you can see there's actually colder pockets of gas that are emerged, and they basically, are happening in this wind. Now, surface densities look completely different. So cosmic rays matter for galaxy formation. Why? Well, because their pressure gradient, they can drive basically, they can exceed the thermal and the RAM pressure and drive the gas out to large heights. And the nice thing about cosmic rays, they don't cool that fast. Therefore, they can basically constantly energize the wind as they sort of rise in the galactic potential. Now, this is the star formation rate, and clearly you can see almost not changed because cosmic rays in the disk don't really interact with the galaxy. So it's only barely reduced by 20%. However, the mass loading factor is increased dramatically by a factor 4 by including the cosmic rays. And if you look at the energy loading factor, that's sort of the new sort of kid on the block. We need to understand the energy loadings to understand the flows into and out of the galaxy into the CGM. This is also increased by adding the cosmic rays by a factor 4. So bottom line, we have developed cosmic ray hydrodynamics, and that's necessary to go to these modern techniques for cosmic ray transport, because you need to actually self-consistently model the diffusion coefficient. If you don't do this, you get the wrong answer. That's what we did in the past, and I think that is a pledge to really move on to the new models for cosmic ray transport. And this self-generated diffusion coefficient naturally emerges from this cosmic ray wave interactions I just explained to you at the beginning. And then adding this to galaxy formation requires you to not only model sort of a broad brush galactic model with a lot of subgrid, but to really self-consistently model the multi-phase structure, the hot, the warm, and the cold phases, because they matter. So cosmic ray barely impacts the ISM or star formation because of the strong ion-neutral damping, which weakens the cosmic ray coupling. But cosmic rays then can drive powerful galactic winds in the regions where nonlinear Landau damping is weaker and can sort of maintain a higher level of alpha waves. And this causes increased mass and energy loading factors. Thanks.